All right, good morning, everybody. I bet you had a nice Thanksgiving holidays. Okay. Um, I think exam 3, the scores already uploaded. You guys might know, right? You guys did very well. The average, I think I forgot to upload the average and distribution. I will do it after class, right? Average, I think 45 something, so very good. 45, right? So, all right. So now we start talk about the new stuff, and for the final exam, and the new stuff will cover like 70%, right? And 30% will be on lipid metabolism and the carbohydrate metabolism. And amino acid metabolism and protein synthesis degradation part will not be covered in the final exam, right? And also I'm thinking to set up the alternative final. The date I'm thinking December 16th. Would that be okay for everybody? So the regular date, I think 21st, right? And we're going to set up the alternative day, December 16th, probably morning time, right? And I think that's all for the final. If you guys have any questions, then you can ask me later, right? So let's start talking about the fuel utilization. So this session actually, I think it's pretty much like a review, what we have learned previously, on the carbohydrate, lipid, and protein metabolism. Now we thinking about more details in terms of the timing, when we utilize, the different metabolic fuels, and also it's important concept that we need to learn from this section. First of all, is that different tissues utilize different energy fuels during the fasting and fat condition that I think we already emphasized this a lot before. And the second thing is it's going to talk about the branching points in metabolism. So branch point means that the specific substrate is very important that connected multiple metabolic pathways, right? We're going to learn about this. And also specific fuel metabolism. Here we're talking about specific tissues like brain, liver, kidneys, muscle, and other tissues, and how this tissue utilize, what type of fuels are utilized in the different tissues in fat and fasting conditions. And lastly, we're going to cover the adipose tissue function in fuel metabolism. So adipose tissue usually, I think traditionally people just thinking, as just stored fat, right, stored energy. And now I think adipose tissue, the way that we're thinking is totally changed. Adipose tissue is actually very active metabolic tissues. Not only just store energy and release energy in fasting condition, adipose tissue or adipocyte can secrete very important hormones and factors that can regulate whole body metabolism. So we're going to talk a little bit about adipose tissue function in metabolism. So first of all, what are the metabolic fuels? The definition for the metabolic fuels is that the metabolic fuel is a circulating compound that can be taken up by tissues for energy production, right? So two important points that you need to remember that, first of all, metabolic fuels has to be a circulating compound. That means that, can be available in the circulation. And secondly, these metabolic compounds can be metabolized to produce energies, right? Now the second question, what are the major fields from what we have learned from this class? So thinking about, we have like five bullet points. So that means we have a five answer, and five metabolic fuels, the five compounds that are considered metabolic fuels. That means our body can be utilized for energy, and these five compounds or metabolized that's actually present in the circulation. So can you guys give me a list of the metabolic fuels that you're thinking based on the definition? Yes. Yes, glucose. And second, right, glucose definitely, right, present in the circulation and can be picked up by tissues and metabolized, produce ATPs, right? And second, we talk a lot, right? During fasting, what kind of nutrients or molecules that cells, tissues use for energy for ATP production. Yes, ketone body is one of them. And fatty acids, yes. And what? Two more. Yes, amino acids. One more. That's very important. During the fasting, what about our tissue use for energy? Says that? No, glycogen is not present in circulation, right? Glycogen is able to, provide energy by breaking down. Close, yes, triglycerides and triglyceride breakdown. Yes, free fatty acids, right? So, oh, you said fatty acids? Oh, I don't know. Let me see. Sorry. Yeah, glucose, fatty acids, triglycerides. Yeah, you're right. I'm sorry. And ketone bodies and amino acids, right? You guys right. Great. So 5, right? Glucose, fatty acids, triglyceride, ketone bodies, and amino acids, right? These 5 compounds are present in circulation, can be picked up by tissues and break down or metabolize, produce ATPs. So these are the metabolic fuels that our body can use for energy production, right? And the other important concept is not all metabolic fuels are available at the same time. What does that mean? Thinking about fat fasting conditions, right? Our body utilizes different type of metabolic fuels. For example, in fat condition, what are the major metabolic fuels our body uses? In the fat conditions? Yes, glucose. What about the fasting conditions? Free fatty acids and ketone bodies, right? And also amino acids. So, and in other words, in the fat conditions, our circulation or our blood, have relatively low ketone bodies, right? Because we don't need to synthesize ketone body used in the fat condition, but we have very high levels of glucose. And fasting, free fatty acids levels also elevated, right? So these 5 different compounds, again, is not always available at the same times, right? Depend on fasting condition. And then the 2 sources of metabolic fuels. So metabolic fuels can be categorized exogenous and endogenous. So exogenous means that the energy fuels that we can obtain from the diet, right? So this will be the major metabolic fuels in the fat conditions. Endogenous fuels that from the body, either we break down the stored energy or we can make the metabolic fuels, right, during the fasting condition. So the endogenous fuels are the major fuels in the fasting conditions, right? So in terms of a endogenous fuels, we can further divide it into two categories. The first is this called stored fuels. So give me like a list of the stored fuels that our body can use during the fasting conditions. Glycogen, right? And triglycerides, and last, proteins, yes. So stored fuels that our body can use during the fasting conditions, triglyceride, which primarily is stored in adipose tissue, right? And glycogen stored in two important tissues, right? Remember, liver and muscle, and the protein. So protein, I think a major, mainly stored in the skeletal muscle, right? When, during fasting, maybe we can break down protein and release amino acids from muscle and utilize by other tissues. And the second category is of endogenous or stored energies, or endogenous fuels, fuels made by the bodies. So we have 2 points here. What are the two main metabolic fuels that our body can make? See that? Ketone bodies, yes. And the other very important metabolic fuels that our body can make during the fasting conditions. Glucose, yes, glucose and ketone bodies, right? So glucose made from the non-sugar precursors through the gluconeogenic pathways, and ketone bodies made from acetyl-CoA, remember, right? And by the liver. And glucose can be made by 2 tissues, right? Liver and the other one, kidneys. And ketone bodies only made by the liver. So we kind of just, review, right, the concept that we learned, but just kind of reorganize, a different way to understand the metabolism. Okay, so, and during the fat condition, when we have adequate supply of macronutrients, what is the major fuels utilized by all tissues? Glucose, yes. Glucose is a major fuel that is utilized by all the tissues in the fat conditions. And during the fasting, when we don't have enough nutrients from the diet, so the body adapt to keep, first of all, to keep blood glucose level within the normal values, normal range. This is very important for the brain and other tissue that cells can only rely on the glucose for energy, remember, right? For example, red blood cells. And also provide, enough energy for basic functions or for survival. So in the fasting conditions, our body try to adapt to fulfill this kind of needs, during the fasting, to keep blood glucose level, to maintain the basic functions of tissues, and to be survival. And this slide, I just wanted to talk in the fasting conditions, kind of balance between the store energy and use stored energy, right? So in the fat condition, our body usually stored energy, right? Try to store energy for the use during the fasting condition. And during the fasting conditions, our body, the auto metabolic pathway can be activated to utilize the stored energies. So in the fat condition, the body stored excessive energy first in the form of a glycogen, right? And second, in the form of triglyceride. So these are the two major stored energy that can be synthesized or stored in the fat condition. And fasting conditions, what our body need to do is mainly to spare glucose, because the glucose is very important, normal range of glucose, right, levels, very important for brain and other tissues, and also spare amino acids. So during the fasting, spare glucose and spare amino acids are the main things. So that means we utilize the stored energy and meantime also synthesize fuels, right? If stored energy is not enough to provide energy, then we also need to make energy fuels. So the first, we start to break down glycogen, right, to glucose and supplies glucose to the other tissues. And second, we make glucose if glycogen is not enough, if we fasting for a longer time. So second thing is to make glucose. Gluconeogenesis will be activated. And the third, if starvation is still prolonged, then we need alternative fuels, right? We try to spare glucose. So we need to break down triglyceride to release fatty acids and for the energies. And lastly, longer starvation, for example, more longer than 2 days, then our bodies start to make ketone bodies, right? So just kind of, the timing of the fuel utilization. First of all, you need to break down glycogen because it's quicker, and we have also a lot of storage in glycogen in the liver, right? So can break down glycogen is the first thing, and then make a glucose the second thing. Then the third is to break down triglyceride and utilize fatty acids as energy. And finally, then we make ketone bodies and also break down some protein to release amino acids for energy fuels, right? Okay, so something that we already talked about, these three macronutrients, they can be interrelated, sometimes can be interconverted, right? Remember? So the first question is, can protein be utilized to make carbohydrate, glucose? Can amino acids be used for making glucose? Yes or no? Yes, right? Gluconeogenesis, remember, right? We use some glucogenic amino acids can be used for synthesis glucose, so gluconeogenesis, yes. And the second question, so can carbohydrate be used to make fat or fatty acids or triglyceride? Yes, right? Through which pathways? Carbohydrate, glucose be utilized to make fatty acids. Remember the specific metabolic pathways? Lipogenesis, right? Lipogenesis, yes. And protein to make fatty acids or triglyceride. No or yes? Yes, right? So protein can be utilized for making carbohydrate and also can be used for make fatty acids or fat, and carbohydrate of course can be used for making fat, right? So everything, carbohydrate and protein can all be able to metabolize and to convert it to fat, right? Now the opposite way. So can carbohydrate or glucose be used to make proteins? Is there any type of metabolic pathway that exists to convert carbohydrate to protein? No, right? No, okay. And what about fat or fatty acids can be converted to protein? No, okay. And what about fat to carbohydrate? Yes or no? Okay, let's see. No, carbohydrate cannot be converted to protein, and fat cannot be converted to protein. Fat can not be converted to carbohydrate. Question mark. All right? With the exception, glycerol and propionyl-CoA. Remember, glycerol is one of the gluconeogenic precursors, right? So these two type of fat lipids that can be utilized to make glucose, all right? So let's talk about this, specify the type of fat, glycerol, and how glycerol and propionyl-CoA can be used to synthesize glucose. Right. First one is glycerol. Remember, glycerol is coming from the hydrolysis of triglyceride, right, during the fasting condition. So glycerol levels increase during the fasting, and glycerol can be picked up by the liver and utilized for synthesis, for the glucose synthesis, right, gluconeogenesis. So, and this is the pathway how glycerol be utilized for making glucose. And remember, this is just the two steps, remember, reactions in the gluconeogenesis, right? If we use the glycerol as a precursor for gluconeogenesis. So first of all, the glycerol kinase, which present in the liver, right, to phosphorylate glycerol to glycerol 3-phosphate. This is the first reaction. And second is the glycerol 3-phosphate can be converted to glyceraldehyde 3-phosphate, and by the glycerol 3-phosphate dehydrogenase. And this is, remember, is the metabolized, right, in the glycolysis pathway. Remember this, right? So, and this metabolized can enter the gluconeogenic pathway for making glucose, right? So this is sort of a pathway that the glycerol can be utilized for gluconeogenesis. And the second type of a lipids or fat, like propionyl-CoA. This is the type of the metabolites of all-chain fatty acids and branched-chain amino acids, right? So propionyl-CoA is coming from the oxidation of all-chain fatty acids and branched-chain amino acids like leucine or valine. And this type of lipid molecules can be utilized for the gluconeogenesis, right? So this is the metabolic pathways for gluconeogenesis from propionyl-CoA. So first of all, the propionyl-CoA carboxylase to carboxylate propionyl-CoA to methylmalonyl-CoA. And the second enzyme is methylmalonyl-CoA mutase to convert methylmalonyl-CoA to succinyl-CoA. Succinyl-CoA, remember, is one of the intermediates in the TCA cycles, right? So succinyl-CoA, once enter the TCA cycles, can be converted oxaloacetate, and this then through the, remember the process we call estroprosis and anaeroprosis, right, process. And then oxaloacetate then leaves TCA cycles, enters gluconeogenic pathway for making glucose, right? So just try to remember these two specific type of fat can be utilized for gluconeogenesis, and the the sources of these two type of fat. The glycerol basically is from the the breakdown of triglyceride, and propionyl-CoA is from the oxidation of chain fatty acid. So propionyl-CoA basically is a three-carbon have a three-carbon skeleton, right? It's different from the acetyl-CoA. Acetyl-CoA is a two carbons. It's very similar, the molecules, but propionyl-CoA has a one more carbon. So that's why the propionyl-CoA is able to utilize to making glucose, but acetyl-CoA is not, right? Remember. Any questions about this conversion? Okay. So now let's talk about the branch points in metabolism. So branch point means that it's substrates that can lead to different metabolic pathway in metabolism. That means that specific intermediate in the metabolic pathway that can connect the multiple different metabolic pathways. So, and we wanted to learn four branching points, four substrate or metabolites: the glucose-6-phosphate, pyruvate, acetyl-CoA, and succinyl-CoA, right? So these four metabolic metabolites are very important that connect multiple metabolic pathways, including carbohydrate, lipids, and protein metabolism, right? So I think this is also important, just connect, all the three macronutrient metabolism together. So also I think it's a good way to review the knowledge that we learned, right? So let's talk about the glucose-6-phosphate first. So the pathways that can generate glucose-6-phosphate, thinking about what kind of metabolic pathways that be able to produce glucose-6-phosphate. Glycolysis, right? So glycolysis is one of the pathways that can form the glucose-6-phosphate, and glycogen breakdown, right? Glycogenolysis. So you could break down glycogen can also generate glucose 6-phosphate. And the last one, gluconeogenesis, right? The glucose 6-phosphate also present in the gluconeogenic pathways, right? All right, so now the pathway that can use glucose 6-phosphate, in other words, that glucose 6-phosphate can connect to the other metabolic pathways. Glycogen synthesis, right? Glycolysis and the pentophosphate pathways. Remember, this is the important substrate, right, for pentophosphate pathways. Okay, so second branching point, the important metabolite is pyruvate. So pyruvate is also very important, right? It connected to a lot of different metabolic pathways here. Basically, pyruvate is derived from the metabolism of glucose, amino acids, different type of amino acids, and also can be converted from lactate, right? And pyruvate connect to the TC cycles by converting to acetyl-CoA, right? Remember, this is pyruvate dehydrogenase in the mitochondria. So acetyl-CoA enters TC cycles, right? And acetyl-CoA can also be used for synthesis of fatty acids, ketone bodies, and cholesterol. And pyruvate can also directly convert to oxaloacetate and for making glucose, right, in the gluconeogenic pathways. So just try to connect this using this branch metabolic points to connect all the different metabolic pathways to try making the big pictures, right? Understand the metabolism, the regulation or interrelationship between different nutrient metabolism. Oops, sorry. Now the third branching point is the acetyl-CoA. So acetyl-CoA, do you guys know, right? We emphasize a lot as very important essential molecules that connect the oxidation of 3 macronutrients. And so acetyl-CoA basically is derived from the oxidation of glucose, fatty acids, amino acids, right? And can be either completely oxidized enter TC cycles, or can be used for synthesis of ketone bodies, fatty acids, and cholesterol, and depend on, again, the fasting condition, right? And also different tissues. All right, so last one is succinyl-CoA. Succinyl-CoA is the TC cycle intermediate, right? And these molecules connect the metabolism of branched-chain amino acids and alt-chain fatty acids, right? So succinyl-CoA basically is coming from the oxidation of branched-chain amino acids and alt-chain fatty acids metabolism, and then enter the TC cycles, right? Remember, we're talking about the specific type of lipids, the propionyl-CoA, right, can be used for gluconeogenesis. So succinyl-CoA is connected. It's very important molecule that connect the, these pathways, right? Any questions so far? Okay, so now this slide I just put all 4 different branching points in the glucose 6-phosphate, pyruvate, acetyl-CoA, and acetyl-CoA, and you can see where are these 4 branching points located and how they connected to different metabolic pathways, right? So, like for example, glucose 6-phosphate can be generated from glycolysis or from glycogen breakdown or gluconeogenesis, right? And glucose 6-phosphate can be used for synthesis glucose or can be further breakdown or oxidized to pyruvate and even complete oxidized, right, in TCA cycles. And also glucose 6-phosphate can be converted glucose 1-phosphate for glycogen synthesis and also connect the phosphate pathways, right? And pyruvate, we know that it can be oxidized from the glucose or amino acids and can be converted to lactate depending on the physiological conditions in fasting, for example, right? And pyruvate can also be converted alanine in the muscle, right? In specific in the muscle, and these 2 molecules are very important precursors of gluconeogenesis, right? Through this called Cori cycles, alanine cycles. Remember this, right? And acetyl-CoA and definitely is a key point that can be generated from oxidation of glucose, amino acids, and fatty acids, right? And can be either enter the TCA cycle for complete oxidation during depending on tissues. For example, in the muscle can become completely oxidized to produce ATPs. And in the liver, acetyl-CoA probably will not be completely oxidized, but can be used for generating ketone bodies and cholesterol and also fatty acids, right? Depending on, again, the physiological conditions. And last one is acetyl-CoA. Basically, is from the oxidation of chain fatty acids and branch chain amino acids, and enter TCA cycle can be either for gluconeogenesis in the fasting condition, right? So just try to connect all this metabolic pathway by these 4 branching points, right? Now let's talk about the specific tissue-specific metabolism of energy fuse. So that we already mentioned that different tissues may utilize different energy fuse, and in fact, the fasting condition and different fuse can also, different fuse also utilize in the different physiological conditions, right? So first organ is the brain. So what kind of energy fuse that brain can use? Glucose, of course, right, is the most important, and the ketone bodies, and sometimes brain can also use lactate, but brain cannot utilize fatty acids as an energy fuse, right? And also not much amino acids for energy. And brain lacks the stored energies, not like liver or muscle, right? You have stored energy like glycogen. Brain almost have no like stored energy, right? So it's heavily reliant on the glucose to continuously provide glucose to brain. It's very important, right? So usually about 60% of the glucose that utilized by the brain. The whole body, circulating 60% of circulating glucose actually utilized by the brain. So brain utilizes a lot of glucose, right? And fuels that can be released by the brain, usually lactate. So only in the prolonged starvation, very long-term starvation, that brain will also start to partial oxidize glucose and release lactate, right? So in the most of conditions, glucose usually is complete oxidized in the brain, but only in very long-term starvation, brain also try to spare glucose, to partial oxidize glucose and release lactate. So, and also during the prolonged starvation, ketone bodies are also become very important energy fuels for brain, right? So ketone bodies can be oxidized in the brain, and also I mentioned that during prolonged starvation, glucose metabolized also just restricted to the glycolysis, right? Partial oxidation and produce lactate. Yes.
Would that be with or without like a hypoxia situation?
That's a good question. The hypoglycemia, right? You're talking about.
No, would it solely be if they were in starvation, or would it be depending on if they have low oxygen too?
Oh, that's, well, I think that would be the very, very dangerous condition, right? Hypoxia. I think usually, you're right. So under that kind of conditions, because of the oxygen is not enough, right? So the brain cells will not be able to completely oxidize glucose. It could be one of the reasons, but probably it's not in prolonged starvation under the hypoxic condition, right? So brain will also partially oxidize glucose and produce lactate. All right. So, and what is the brain preferred fuels? Of course, the glucose, right? Glucose is preferred fuels, and also ketone bodies during the very long-term starvation, and lactate only in the pathologic conditions, right? For example, hyperglycemia, when undergoing the hyperglycemia conditions, then brain be able to utilize the lactate. So under hyperglycemia, because the other tissues only goes partial oxidation of glucose, right, to produce a lot of lactate. So under these conditions, the lactate level will be very high compared to the normal condition. So then brain be able to pick up some lactate that produced by other tissues and utilize the energy. So normally lactate level is very low, right? So one definitely is not a major metabolic fuels for the brain. So and other important conditions, I think under the perinatal period, because the brain development, cell development is also required for the requires the lactate for the synthesis of lipids, right? So lactate can also be utilized for the synthesis of lipids, so which is very important in the developmental stage, right? And so at this kind of conditions, brain also pick up some lactate, but not for the energy use, right? Just for synthesis of lipids in the brain. All right. How about we take a break? Another right. Okay, now let's talk about skeletal muscle. So how skeletal muscle utilize the energies in fasting condition, what type of energy fuels that can be utilized um, by the skeletal muscle, right? So first fuels utilized are, just take a guess, what type of energy fuels that muscle can use for ATP production. Glucose, right? And then fatty acids, right? So fatty acid either from the stored source or circulating fatty acids and ketone bodies, right? Amino acids. So muscle is able to utilize almost all type of energy fuels, right? So it's easy, right? And what is the preferred fuel in the fat condition or under the burst of the activities, like we're doing the exercise? What is the preferred fuel? Glucose, yes. Glucose is the preferred fuel for muscle. And what is the major fuel in resting muscle in the fasting condition? Means that this energy fuels meet like 85% of energy needs in the muscle. What type of energy fuels? Yes, fatty acids. Thank you. So fatty acids is the major fuels for skeletal muscle during the resting or during the fasting condition, right? And what type of energy fuels the muscle can release and to provide to the other tissues? Lactate, alanine, and glutamine, right? So lactate, alanine can be utilized for making glucose in the liver during fasting condition, right? So fasting condition muscle release a lot of lactate and alanine for gluconeogenesis in the liver, and also glutamine releases from the muscle during fasting, then can be picked up by other tissue, used for energy and also making glucose in the kidneys, right? Remember, so. All right, so just wanted to remind you again, there's two important cycles that for gluconeogenesis and connect to the that related to muscle, right? For Cori cycles, then you know that the precursors for gluconeogenesis in the liver is the lactate, right? And muscle is one of the providers of lactate for gluconeogenesis in the liver, together with the red blood cells. So muscle is very important provider of the lactate for gluconeogenesis during the fasting conditions. And the other important cycles for gluconeogenesis, alanine cycle, right? Muscle also provides alanine, which initially converted from pyruvate, and pyruvate can be generated from amino acid metabolism and also glucose metabolism, right? So, and converted to alanine and released to circulation for gluconeogenesis in the liver. So muscles contribute alanine for gluconeogenesis during the fasting conditions. And in terms of the stored energies, and what type of stored energy that muscle can make or can store? glycogen, right? Glycogen is one of the important stored energy in the muscle, and the fatty acids, triglyceride. So muscle is also able to synthesize and store triglyceride, but at the small amount, right? You compare to the adipose tissue. So adipose tissue definitely is a major site for the storage of triglyceride. But muscle is also able to store some small amount of triglyceride and utilize during either fasting or particularly during the exercise we're going to talk about later, right? And in the vigorously contracting muscle during the exercise, the muscle contraction, that the glucose can be partially oxidized to produce lactate and also break down protein to produce alanine. Right? So we just keep in mind, the glucose can be partially oxidized and also can break down the proteins during the exercise. We're going to specific talk about fuel utilization during exercise later, right? Just here, just touch a little bit. And glycogen stored in the skeletal muscle are usually utilized locally, right? Remember we talk about a lot. Glycogen breakdown in skeletal muscle will not be able to release glucose because of its important enzyme, right? It's not present in the skeletal muscle. So glucose 6-phosphatase is the enzyme that converted glucose 6-phosphate to free glucose, and this enzyme is lacking in the skeletal muscle. So skeletal muscle only break down glucose and utilize within the muscle, will not release glucose into circulation. But muscle is also very important contributor to the circulating blood glucose levels through the indirect mechanism, right? We also talked about this before, I think. One is the choline cycles, alanine cycle, right? We just mentioned, by releasing the lactate or alanine for making glucose in the liver. So indirectly contribute to circulating glucose, right? And also can break down the proteins, right? And release amino acids. And those gluconeogenic amino acids can also be utilized to making glucose in the kidney and also in the liver, right? And for example, glutamine can be converted to glutamate by glutaminase, and glutamate can also interconvert it with the alpha-ketoglutarate, right? And alpha-ketoglutarate in the TC cycle, and then converted to oxaloacetate and gluconeogenic pathways. Remember this, right? So again, indirectly by contributing to circulating glucose levels by providing lactate, alanine, and also other glucogenic amino acids. Okay, so now specifically we talk about what is a preferred fuel for the skeletal muscle. So in fat condition, we know muscle prefer to utilize glucose for energy, right? Glucose is a preferred fuel in the fat condition, in skeletal muscle. And during the fasting, fatty acids is the preferred fuel in the skeletal muscle. We know that 85% of energy, right, provided by fatty acids during the fasting condition. And under the muscle contraction, exercise conditions, and glucose still is an important energy fuel. And under prolonged starvation, mean that not just a couple hours starvation, but days, several days starvation. This type of a prolonged or long-term starvation, then muscle will prefer to utilize fatty acids, ketone bodies, right, and also amino acids. And glucose utilize, but just spare, just go to a partial oxidation, right, during the prolonged starvation. So again, in the fat condition, glucose will be the main energy fuel, and during just a short-term starvation, fasting, fatty acids is a major fuel, and prolonged starvation, started using more and the other alternative fuels like ketone bodies and amino acids, right? So in the fat condition, usually muscle will not utilize fatty acids for energy fuel, right? Okay, now kidney. So kidney is also the tissue, the organ that can utilize almost all the different type of energy fuels for ATP productions, like glucose, fatty acids, ketone bodies, lactate, and glutamine, right, can also be the energy fuel for kidney. And also kidney can almost oxidize all the energy fuels. For example, glucose can be oxidized completely through glycolysis and TC cycles, right, in the kidney. And of course under the fat condition, right, and fasting condition, almost all the tissues will go partial oxidation, right, of glucose. Try to spare, carbon skeleton. And fatty acids can be oxidized through the beta oxidation, and ketone bodies that can be oxidized through TC cycles, right? Lactate and glutamine can also be complete oxidized through the TC cycles when they are used for energy production. And we also know kidney is important, the organs for gluconeogenesis, right? And particularly during the prolonged starvation. Remember the 24 hours later after starvation, right, our kidney start to making glucose. Gluconeogenesis is very active in the kidney after 24 hours starvation. And it is the only tissue that can make a glucose besides the liver, right? So our body, liver and kidney will be able to make glucose. And also important thing is the glucose 6-phosphatase is present in the kidney. That means kidney make glucose and be also able to release glucose into the circulation, right? Intestine. So small intestine, do you guys know what type of fuels the small intestine use? Right? A little bit different from the other tissues, right? Basically, I think glutamate are the most important energy fuels for small intestine, and glucose are relatively utilized at a small amount compared to the glutamate. So 20% of energy is from glucose, right? And the other maybe 60% or more, 70%, 70% energy from glutamate, right? And the rest of energy can be will not see the sorry, I would take my, my the words back. So in the fat condition, right, 20% from energy from glucose and 80% from amino acids, glutamate, right? And during the fasting condition, of course, the ketone body fatty acids will also be able to be utilized by small intestine as energy, right? Does that make sense? Right? Okay. So, and glucose is usually partially oxidized to lactate in the small intestine and then released into circulation. And glutamate is also partially oxidized into form lactate, pyruvate, and alanine, right? So small intestine be able to release lactate, pyruvate, and alanine, right? Because of the partial oxidation of these amino acids and glucose. Any questions? Okay, so yeah, so glutamine metabolism is, in the fat condition in small intestine, right, can produce the CO2, of course, complete oxidized and produce CO2, alanine, pyruvate lactate from the skeleton, and also ammonia, right, and alanine from the amino group, right? Remember the amino acids as the carbon, carbon skeleton and also amino groups, right? You learn from the amino acid metabolism. Okay, so colon is very special. They have a unique metabolism. So the energy utilized by colon basically is derived from the is a butyrate. Butyrate is the short chain fatty acids, right? It's derived from the fermentation of dietary fibers and the resistant starch by the microflora, right? So in colon, a lot of microflora present, right? In the colon, so then can metabolize the dietary fibers and produce these short chain fatty acids like butyrate. Butyrate is a major energy fuse for the colon, right? All right. Red blood cells, it should be pretty easy, right? It's only utilize glucose for energy, cannot utilize the other things like, other energy fuse. And reason you guys know already, right? And only not two things, only utilize glucose for energy, and second thing is partial oxidized glucose to produce lactate, right? We're not able to complete oxidized glucose. So this is the two main characteristics of energy metabolism in the red blood cells because of it lacks mitochondria, right? And of course, the other pathway that red blood cell can do is the pentose phosphate pathway, right? It's very active, this pathway in red blood cells, because the membrane, red blood cell membrane requires a product of the pentophosphate pathway to maintain the integrity of the red blood cell membrane, right? Remember. All right. Liver. So liver in the fat state, 20% of blood glucose pick up by the liver, right? And in the fat state, what liver is going to do with the glucose that pick up from circulation in the fat condition? Do you guys know? Yeah, stored as glycogen, right? So in the fat condition, the 20% of glucose that initially absorbed from the diet in the circulation and picked up by the liver for the synthesis of glycogen and stored in the liver. And also, if have excessive glucose can also be converted to fatty acids through lipogenesis pathway, right? And stored in the form of a triglyceride in the liver. Or if we have lots of fatty acids or triglycerides synthesized in the liver, then can be released into circulation by the VLDL, right, lipoprotein, to the adipose tissue and stored in the adipose tissue. And glucose can also be utilized to metabolize through the pentose phosphate pathway, right? And so stored glucose and fatty acids, right? Just like I already mentioned, right? In the liver. Again, the liver is able to store triglyceride, again, also a very small amount, right, compared to adipose tissue. But under the disease condition, for example, obesity or diabetes, patient, the liver store a lot of triglyceride and causing the fatty liver disease, right? Because some metabolic dysregulation that triglyceride either to make too much triglyceride or triglyceride cannot be exported the liver, right? Remember this fatty liver disease. But under the normal conditions, we don't expect to have a lot of triglyceride stored in the liver, right? In the fasting conditions, and liver is a major source of endogenous energy fuels. So this is a very important concept, right? Fasting condition, liver is a major source of endogenous energy fuels. Why is it an important endogenous source? What liver will do to provide energy during the fasting conditions? And how liver provide energy? Yeah, glycogen breakdown. And what else? Gluconeogenesis, yes. And ketone body synthesis, yes. So very important organ like liver, right? During the fasting condition can provide glucose by breaking down glycogen, by making glucose gluconeogenesis, and also by making ketone bodies and release ketone bodies, right? So it's very important. So if something is wrong with the liver function, some disease liver function dysfunction, what will significantly impact the energy utilization, right? Particularly during the fasting conditions. And in terms of fuels that can be utilized by liver, so the liver contributes a lot of important energy fuels for other tissues, but liver itself also need energy, right, to function or to making to perform this kind of activity. So energy fuels that are utilized by liver is also a little bit different from the other tissues. That first of all, it's amino acids, right? So it's not actually glucose, it's amino acids. So amino acids and then glucose are fatty acids. And all these three energy fuels are partially oxidized in the liver. So the preferred fuel for the liver is actually alpha keto acid, right? And this is originally from the amino acid metabolism, right? Alpha keto acid. So alpha keto acid from amino acid metabolism is a major energy fuel or preferred energy fuel of the liver, right? So liver primarily utilize alpha keto acid as the energy. But of course it also utilize glucose fatty acids. And glucose fatty acids also undergo partial oxidation, right? For glucose, you just try to spare the carbon skeleton, right? And for fatty acids, goes partial oxidation means that just stop the acetyl-CoA, goes beta oxidation and generate acetyl-CoA, and then this acetyl-CoA will be used for ketone body synthesis during fasting conditions, right? So the liver does the partial oxidation of these nutrients have the reason, right? Partial oxidation glucose just for you save the carbon skeleton, right? And partial fatty acids oxidation is to make ketone bodies, right? Okay. And what kind of energy fuel that liver can make and release into circulation? Glucose, of course, right? Through the both glycogen breakdown and gluconeogenesis, and ketone bodies and triglyceride. So liver, again, is a major endogenous energy fuse, right? Endogenous source of energy fuse by releasing glucose from glycogen breakdown, gluconeogenesis, and ketone bodies and triglyceride. Right? And this energy fuse, of course, is again, if we connect it to the fat fasting condition, right? So in the fat condition, basically liver releases triglyceride, right? Will not release much glucose or ketone bodies. And during the fasting conditions, and liver, makes a lot of glucose, ketone bodies, and release this energy fuse. All right. Any questions? No? Okay. So I think the next two slides, I just put all the metabolic pathways and a few metabolism in the liver in the fat fasting condition. Try to emphasize a little more about energy fuel utilization in the liver. So first of all, we all know that in the fat condition, right, we eat a lot of, we obtain a lot of nutrients, including glucose, fatty acids, and amino acids, right, from the diet. So for the glucose, that first of all we go the glycolysis pathway, right, to make pyruvate, and pyruvate can be further oxidized to acetyl-CoA, and I making this kind of dot arrow because of to indicate that the activity to go this pathway is relatively low or small, right? So majority of the glucose being metabolized to pyruvate, acetyl-CoA, and then go to the lipogenous pathway, right, to make fatty acids, and most important, and to make triglyceride, and release into circulation in fat condition, right? And I don't know why I try to point the glucose first. Let's see. And most important pathway is that pyruvate that metabolized from glucose, right? And be converted to glucose 6-phosphate and to make glycogen, right? So this is the most important pathway in the fat condition for glucose, dietary glucose, remember, right? And also secondary pathway is that to making fatty acids, lipogenesis, right, in the fat condition. And then in addition to the glucose, and we also observe, right, and digestion of absorb the amino acids. So the amino acids, lots of amino acids can be metabolized in the liver and converted to pyruvate, and the pyruvate can go to the similar two pathways, like either for the converted glucose to store in the glycogen in the form of glycogen, or can be converted to the fat, right, and to triglyceride. And some of our amino acids can will not metabolize to pyruvate, but converted to alpha ketoglutarate, right? So this set of amino acids will metabolize to alpha ketoglutarate and succinyl-CoA and enter TC cycles for making glucose, right? So different pathway, making glucose depend on which type of amino acids. So in general, that in the fat condition, that the amino acids can be converted to glucose and stored in the form of a glycogen in the liver, and also can be converted to fatty acids, right, and fat in the fat condition. And of course, some of the dietary fatty acids can also directly be uptaken by the liver and making triglyceride. So this is something happening in the fat condition, right? And in the fasting condition, of course, the glycogen breakdown is most important on first, occurred during the fasting, right? To break down glycogen, release glucose directly into the circulation, and also gluconeogenic pathway is activated, right? And so glycerol or the lactate or other glucogenic amino acids can be utilized for making glucose. And again, the glucose only goes partial oxidation, right, to produce lactate and convert it back to the pyruvate. And this pathway is relatively weak, right? And relatively, activity is relatively small in the fasting condition. Glycolysis will not much, acetyl-CoA be generated during the fasting condition, right? And fatty acids will be the important, the energies, and then pick up by the liver and goes beta oxidation, right, and generate acetyl-CoA. So under the fasting condition, the acetyl-CoA, the majority of acetyl-CoA actually is from the beta oxidation of fatty acids, right? And for the fate of fatty acids, again, in the fasting condition, the majority of a fatty acetyl-CoA will be utilized to make ketone bodies and release into circulation, right? And only very small amount of acetyl-CoA be fully oxidized, right, in the liver. So, and the other pathways also relatively low, activity is low in fatty acids from the lipolysis in the adipose tissue during fasting condition, right, can also making, the liver can pick up for triglyceride synthesis. This pathway is relatively low compared to the beta oxidation pathway, right? So again, fatty acids level will be high in the fasting condition. Basically, it's from the fatty acid oxidation, right? And a lot of fatty acid picked up by the liver is to oxidize and to make ketone bodies, right? And not much for complete oxidation, or not much for triglyceride synthesis, right? That makes sense? Okay. All right. Not sure. Maybe we'll just try to finish this slide, and then we have the reformer writing, right? So adipose tissue. Adipose tissue be able to utilize glucose and triglyceride as energy. And in terms of a pickup, metabolic fused by adipose tissue in the fat condition, adipose tissue is able to pick up fatty acids, right? And this fatty acid will not be utilized as energy in adipose tissue. Instead, the fatty acids being converted to triglyceride, right? And stored in the adipose tissue in fat condition. And glucose is also picked up by adipose tissue, but utilized as energy, but mostly is converted to glycerol 3-phosphate, remember, right? So, glucose being picked up by adipose tissue in fat condition and metabolized to generate glycerol 3-phosphate for the triglyceride synthesis, right? It's a backbone, glycerol backbone. And during the fasting conditions, the fatty acids, lots of fatty acids break down from triglyceride and released into circulation. So adipose tissue is a major source of fatty acids during the fasting conditions, right, for the energy fuel utilized by other tissues. And glycerol, of course, also is released from fatty acids, but utilized for glycerol for the gluconeogenesis. And lactate can also be released, but not, I don't think it have a large amount, but you still have some lactate released. Almost every tissue will release lactate, right, during fasting condition because of a partial, partial glucose oxidation. So, all right. So let's have any questions.